Dear colleagues, welcome to this presentation. I am Gianni Picchi, and I will talk to you also on behalf of my colleague Carla Nati about the performance of dedicated UHF RFID tags in timber automatic identification. Well, this topic is interesting, or we consider it interesting, because tracking and tracing services are more and more popular and important, and the precision forestry, or the future developments of precision forestry. Tracking and tracing are basically the same service. In tracking, we are monitoring in real time the position or the performance of an item or a machine. And in tracing services, we go back, we retrieve this data afterwards, and we go back in time, the supply chain up to the origin of each product. So these services can return an interesting economic value because they provide us value recovery services, management of inventories, process optimization, invoicing, and of course, certification of timber products. There are a number of technologies, and more specifically focusing on single log or single item tracking. There are two main technological options. One are the optical systems. They are quite common. There are a lot of solutions, and some of them are already in commercial stage. Others are still prototyping, but they all have in common the necessity to use optical system that can see and detect something, some aspect of the item we want to track. The most simple solution will be the processor you can see here is a processor with spraying capacity, so can spray colors on the crosscut section of the logs that is producing, up to 3 colors in this case. But of course, information is very limited. We can segregate different assortments, but not assign an information to the single items. For this, we need alphanumeric codes with unique identifiers for each product. And when we go more in automation, we will have barcodes or QR codes. Those can be printed on labels or tags. You can have an example of a commercial tag. Other prototypes have processor heads capable of printing directly the barcode on the crosscut section. So it's an evolution of the processor we saw before. A Swedish company is providing an attachment to processor heads, which is actually punching into the wood, impressing into the wood a code, which, thanks to the geometry of the different hammers, corresponds to a unique identifier. You can see here an example of identifiers. And the most technological advance in optical systems is fingerprinting. In this case, optical images are elaborated, and the information regarding the unique characteristics of each log, the crosscut section of the log, so the shape, but also the ring distribution, is used to identify single items throughout the supply chain, from the processing stage to the yard and the end user. An alternative to optical systems are electronic systems, and more specifically, radio frequency identification systems, also called RFID. We are particularly interested in RFID because they have a number of useful features in forestry supply chains. Well, one of them, very important, they don't need line of sight or proper illumination to allow detecting of the codes of the barcodes, for instance. They can be read at further distances, greater distances compared to optical systems, so several meters in optimal conditions. And they allow for bulk reading, meaning that I can scan a number of items with several tags attached on them, and I can detect all of them together in a unique action. That it can be very, very useful. These systems have been already tested in several conditions, several steps of the timber supply chain. So from marking standing trees for a long time to hauling whole trees, for instance, with cable yarders, or marking the logs produced by a processor head. But what is probably most important and still challenging, so still a constraint to the application of RFID in timber supply chains, is bulk reading. The key point in bulk reading will be at the mill gate, where a truckload of timber is entering the mill and is detected automatically by a scanner, an RFID scanner, which identifies all the identities of the logs which are entering into the yard, and then simplifies the yard management, allows for automatic invoicing, and so on and so forth. Several services can be imagined and applied. The challenge is probably due to a number of reasons. One of them definitely is the unfavorable reading angles. Here you have an example. This is a truck entering, and due to the fact that we have to create a full tunnel or a bridge for placing the antennas, the antennas, the tags will be placed necessarily on this area, the crosscut section, which is parallel to the antennas and the wave that can be emitted. This creates unfavorable conditions. We will see more in detail later for detection of the tags. Another problem can be tag collisions. This is basically a software problem, because when I emit an interrogating wave, then I have answer from a lot of tags together, and may happen that the stronger signal cover and hide the weaker signal which are not detected, even if they're there, and even if the tag is trying to be identified. Another problem, which sums up with the others, is the limited remit time. We want the truck to pass slowly, but pass through the gate without stopping, and then go unloading, reducing as much as possible the time, the idle time that we need for the identification of the tags. Just some information about RFID systems. They are composed by a reader and antenna, can be together or separated, and a tag, or RFID tag, which is attached to the item that we want to identify, in this case, a log. Here, a close-up of the RFID tag. It's basically composed by an antenna, a metal antenna, and a microchip, which is storing the information, in this case, a very low memory, which represents the unique identifier of my tag. This system that I'm showing you is a passive RFID system, meaning that this tag has no power source by itself, but is powered by the interrogating wave. So when I'm emitting the interrogating wave, this reaches the antenna of the tag, which gathers the energy to activate the chip and to return a signal. The signal is the answer containing the unique identifier of the tag. There are several factors that may affect the performance of these RFID systems. One very important is the angle of reading. Here I play some very rough example and very rough explanations. Of course, the phenomenon is much more complex, so forgive me for being very too simple in this explanation. But going to the angle, when I have a reader facing a tag, if I have different angles, for instance, in this case, 0 or 45 degrees, I will have a different behavior of my wave, both the interrogating and the answering wave, the answering power signal. And in this case, with an angle, it will be much weaker than this case, which is the optimum. So the two antennas are facing each other. Of course, another factor will be the distance. So the greater the distance between the reader and the tag, and the weaker will be the signal. Another very important factor is the presence of water and metal. Those are the main elements. Other elements can disturb the reading performance, but water and metal are very important. Water, because timber is composed, fresh timber is composed by about 50% of its weight by water, and water has dielectric properties that absorb the energy of magnetic resonance waves. So in this case, electromagnetic waves, sorry. So in this case, the presence of water will reduce the power of both the emitting, the interrogating, and the answering antenna waves. Metal instead is reflecting the electromagnetic waves, so it can prevent completely the readability of a tag that is behind a metal obstacle. Another aspect that is important to consider when we want to achieve bulk density is how trucks are layout of trucks and how the timber is loaded on trucks. On the left side, you can see a specialized timber truck in European conditions. And you can see that it's basically bare loading areas with the poles and nothing else, just to minimize the weight of the truck and maximize the payload. And this is the ideal condition for reading RFID tags, where the unique challenge will be the shell protecting the cabin of the truck. In Italy, unfortunately, it's quite common to have multi-purpose trucks, since in central southern Italy, mostly we have different type of assortments. So they're transporting maybe just timber and firewood, but quite a lot of firewood, very short, or pulpwood, as in the case in the picture, with length of 2.5 meters or less than this. And those trucks will have walls, metal walls, and shells also in the trailer. So will represent a much more challenging condition for reading all the RFID tags attached. We must say that RFID tags and traceability systems in general make sense only with high valuable timber products, timber assortments. So we're looking for big, long logs, which will be typically the case that is transported with a specialized timber truck. In this case, we are trying to identify the tags located in 4 positions, which are basically these planes, the pile of logs, the crosscut sections, where the tags are located. So going to the material methods, in this study, we tested a new RFID tag model, which had been developed specifically for timber supply chains, as the Sundog tag, developed by a Texan company, and is based on a non-metal staple used for carpentry or wooden construction, where they added a chip and 2 wire antennas. It's quite different than the layout you saw before for a typical RFID tag, and this is why it can be very promising for timber supply chains. Compared to the other antenna, the other tag, sorry, the antenna will be basically the area included between the 2 wires. We compare this RFID tag with a common commercial RFID tag that we already tested successfully in timber supply chains in the frame of an European project. Why we expected this tag to be more performing, why it was interesting in the study? Because this tag has the antennas protruding from the crosscut section, so it is possible to read it effectively, even if we are placing our reader by the side of the log, so with the emitting wave parallel to the crosscut section, which would be the less favorable condition for the Shortdipole. Here you can see the typical graph of reading performance of an RFID tag. And this means that when I have a 0 angle, so I'm facing directly the flat area of the antenna of the tag, I have the maximum signal returned. When I'm reading from 90 degrees, I have the minimum power return to the reader. So I have the minimum possibility to acquire the information from this tag. For setting up properly the test, we perform some preliminary tests where we try to simulate the area, the loading area of a truck with this wooden structure, where we attach 46 RFID tags, 23 Sundog and 23 Shortdipole model, and they were attached together side by side. And we tested several aspects, such as the collision risk. So if some tag was not readable because of the collision phenomenon, and the proper layout of antennas, and the effect of different positions of the sound of tag. We tried also to reduce or to simulate the presence of a wet material behind antennas with wet clothes placed behind the antennas, but clearly this is not the amount of water that a truck will carry. So it was just an attempt. We were satisfied with the preliminary tests, and we went to the forest. We applied the tags at roadside. For the Sundog, we used the dedicated stapler powered with CO2. It's a very handy and very fast solution for applying tags, while the Shortdipole were applied manually with a common stapler using aluminum staples. All the tags were applied in couples on the crosscut section, not necessarily in the center of the crosscut section, but generally in that position, in both crosscut sections of all the logs. We contracted a truck for transportation. In our area, dedicated timber trucks are not easy to find, so we had to contract a multi-purpose truck, and we asked the driver to remove as many walls as possible. This is the result. He loaded 31 logs, in the trailer and 25 on the truck. And the total was, so the resulting load in RFID tags was 224 RFID tags, 112 per type, Sundog and Shortdipole. In this configuration, this case, we expected to have troubles identify the tags behind these two shells in the trailer and in the truck, and in the proximity of the walls, the side walls that remained on the truck. We went with all the equipment to the facility of the logistic contractor. We installed the RFID bridge, the scanning gate, and we started the tests. For the test, we experimented 3 antenna configuration, which were the treatments. So the first was with 0 degrees angle. Basically, the antennas were facing each other. The antenna were operated in couples, so 4 circularly polarized antennas were installed on 2 poles, and they were operated by an industrial reader powered, set at the maximum reading power, 4,000 milliwatts. 1,400 milliwatts, sorry. So, the truck was passing through this gate. We replicated the reading 5 times, and then we changed the setting for 30 degrees reading. Again, 5 replications, and finally 45 degrees. By increasing the angle, we were expecting to achieve a better reading angle of the RFID tags, but to increase the reading distance, so to gain answering signal from one side, but to lose it due to the distance. So the result was not straightforward. We added to this test a manual reading test. In this case, we used the same reader, but equipped with a single circularly polarized antenna, small device in this case, which was installed on a 3-meter telescopic pole. So we manually created a movement where we tried to cover quickly all the area of the crosscut sections of the logs in the truck. The result, very briefly, in this table, we just present the tags, the number of tags that could be detected always in the 5 replications. So the result that we desire, 100% readability of all the tags. We can see in green the Sundog, and in blue the Shortdipole. Going to the total results, we see that the difference between Sundog and Shortdipole was enormous. I would say too much, because in preliminary test there was a difference. So Sundog had a better performance, but not this enormous difference. So we think that we had some collision problems, and that the better performing Sundog were so powerful that they were covering basically the signal of the Shortdipole, and so we had a collision that could hide a good share of the Shortdipole signals. In detail, just focusing on the Sundog, 30-degree angle, it provides better performance. and we get to 83% of the tags that could be detected always. So in all the 5 replications, but 13% of the tags were never detected. So we are still relatively far from the goal of 100% tags always detected. This result is, on the contrary, achieved with a manual reading, where in spite of the metal walls that we could not overcome, so we had to try to get to the logs, to the crosscut section, but we could not really get close because of the side walls. Still, we got 100% readability for the Sundog and 90% readability for the Shortdipole tags. So that's a very good result. It is interesting to observe that the critical areas that we expected, so the 2 front areas with the metal walls, did not behave in the same way. So in the truck area, definitely we had a lower reading rate. It's also the only case where we have a statistically significant difference. So front and back of the truck have a much lower reading for the front area, which is what we expected due to the presence of walls, front and side walls. While in the trailer, we didn't have this same behavior, and in some cases, the front area even performed better than the back. So that is an interesting case, probably because of the reflection of the metal wall, which was in a moment shielding, but from a different angle was reflecting the interrogating wave and the answering wave. So going to conclusions and to the end of the presentation, 100% detection is already possible. So the whole supply chain could be achieved, but with manual systems. The manual reading took 90 seconds, about 90 seconds for the whole tracks, for the 4 reading areas, which is not a big deal, but still requires the presence of an operator for this operation. This is not what we want. We want to get to a fully automatic system that can allow us to have the truck passing through a gate and having all the tags detected. So this will require further development, further study. In our plans, we will test different timber trucks with different configurations, namely dedicated timber truck. We will test also different antenna configurations and maybe different tags, or but we are happy, for instance, with the Sundog performance. And we will test separately the tags because we must now avoid this risk of collision by using a lot of tags with different performances. And of course, which is very important, we will have to test the whole supply chain. So from marking logs in the forest or at roadside to the delivery and storing in the yard of the sawmill. So this is the end of the presentation. Thank you very much, and goodbye.